250 degrees Celsius, the secondary phase formed is tetragonal crystal structure, which is sigma phase. So we can see there are sublattices of, these are the sublattice points of sigma phase. Now from customers we are getting a lot of stringent requirement with higher print. Possible difficulty we face is higher print, high alloying elements like chrome, moly and tungsten. So chrome, moly, tungsten, what it does, it increases the cracking susceptibility of the material. But really is print problem? Yes, and sometimes no. So we have to understand when print is a problem. So print is a problem because of the alloying elements that we add to meet the print number. So why alloying elements? Because the elements we add is chrome, moly and tungsten, which increases the ferrite phase, which subsequently increases the sigma phase, which is hard and brittle. So when cracking happens, it happens at solidification, casting, handling and heat treatment, and it happens at corners, section thickness variation zones, thin wall section zones, under rises. So when the print is not really a problem, when we restrict the addition of ferrite stabilizer, creating limited to control the ferrite. So controlling the ferrite controls the sigma, drastically the brittleness of the material also we can reduce. So methods to achieve print, first we think about addition of chrome and moly because it is easy to add. Yes, it is good idea, print is achieved, but the susceptibility of the cracking increases. So what we have to do? Should I increase the nickel to increase the austenite phase? Yes, it is a good idea, but the production cost with the current scenario is not possible, and it is where we have to control. So what are all the, so to understand the better, we did some prototyping of a simple disc in our foundry. So you can see the left side is a grade 5 disc made with print number 42.33, and the material is having crack under riser where the ferrite is around 54 to 57%. One at the right you can see is the disc which is made of 5A with print number 43.72, but the ferrite what we achieved is 42 to 44. So it is better, it is up to us to control the ferrite by monitoring the chemistry of the material. So these are the elements which you can see can help in increasing the ferrite, increasing the austenite, nickel, nitrogen, carbon and manganese, and they also have their constraints in addition. So other parameter what I can do is to control my heat treatment parameters by optimizing the temperature, time, cooling media and heating parameters. So process and results varies for foundries depending on the production process and methodology. So it is very important for us to understand our process, our methodology and how we process the material and to find the solution out of this. And one more thing what I feel to tell everyone is, if we treat the material as a living being, it will definitely react to us back. So with this, I hope this will be a useful presentation, and I also thank IFC for providing this opportunity to share some of the tips that we can share with the entire foundry industry. And I also thank our management, Mr. Taufik Moidu, who is not able to come because of some health issues. So I thank him for providing this opportunity, and our chief operating officers, Mr. Sabi and Mr. Rajesh, for motivating me, and Mr. Muthu, our quality person, has supported a lot in this project, and Mr. B. Raha, our GM Metallurgy, for their entire support during this project. Thank you.
Thank you, Mr. Aditya. Can we have questions? Yeah.
Hello, my name is Ankit Doshi.
Hello, sir.
We are manufacturer of stainless, we are a stainless steel foundry. So we have observed that in Super Duplex 5 and in 4A, sometimes without any reason, all the parameters are okay. A lot of gas occurs, lot of blowholes kinds. And in the same heat, bigger casting is okay and it comes in smaller casting. So is there any technical phenomenon or any reason for this?
Yes, sir. Coming to this gas porosity with varying section thickness, the main parameter which we have to control is from the pouring. So pouring is the main area, melting and pouring is the main area where we can control these gas holes, because we may have to select the pouring temperature based on the design, based on the wall thickness of the material, based on my molding system, and also we have to monitor our mold. because if our mold coating is not completely cured, or if I am just directly pouring without any curing time, if my coating is still wet, so that will also become a part for gas porosity. And sometimes core gas release is also a problem when it is coming to the mold section. So every parameters that we have to check it for controlling the gases in molding and melting area.
Yeah. That gentleman, yeah, please.
Hello.
Hello, sir.
Yeah. First of all, this was a very nice and informative presentation, so thank you very much for that.
Thank you, sir.
I am Tushar from Siemens Energy. I have a very general question. If there is a alloy steel, say AISI 4140 or 4142, and it is suitable from minus 20 degrees Celsius, and if sample piece is tested at room temperature and property derived, then is it any correlation or some method so we can
Sir,
show
sorry, I can't hear, sir.
Please
Hello.
speak loudly.
Hello.
Yeah.
Is it okay?
Yes, sir.
Okay. It is a general question. If there is an alloy steel, AISI 4140 or 4142,
Okay, sir.
if we test it at a room temperature and some properties we noted down, is it any correlation or any method that we can show that this material is suitable at minus 20 degrees Celsius and the property will be like this based on the room temperature testing? Is it there?
No, sir, it is not possible. Actually, that is why even in our EN requirements and also PED and NARSOC requirements, they ask to test at the lowest operating temperature so that our material will be suitable for any higher temperature beyond that. We cannot guarantee a material by testing at minus 20 and I cannot guarantee the same material for minus 30. So it is not possible, sir. We have to test at the lowest possible temperature to meet the requirements so that I can apply my material beyond that temperature, particular to impact toughness.
So particularly for minus 20 degrees Celsius, we have to derive the test result.
Definitely, sir.
That is, thank you very much.
Thank you, sir.
Anyone else?
Good morning, sir.
Good morning, sir.
I am from Indian Railway.
Yes, sir.
We are manufacturer of rail wheels for coaching and boxing.
Okay, sir.
We have pressure casting. Sometimes we are getting slag in middle order. What is its problem and how I can avoid it?
Sir, that's what I told. To understand such process defects, we have to study our entire process because the process varies from foundry to foundry. So that to understand why the slag is forming, we have to start studying from our melting process. So whether we are doing correct deslagging process, whether the slag in the ladle is coming into my material, whether any slag is forming inside my mold, because when I expose my material to the atmosphere, automatically
we are using graphite mold. It is a permanent mold.
Okay, sir. But I don't have idea on that actually.
Thank you, Mr. Aditya.
Thank you, sir.
Thank you very much. Okay. This will be the last question, or otherwise afterwards you can have a one-to-one interaction with the speaker.
Yeah, I was a bit surprised to see that in your presentation you mentioned that cracking is because of, root cause for cracking is the metallurgy. But there are literatures for superplus that heat treatment plays very important role in order to control the cracks. So your views on heat treatment, because this could be one of the possible reasons
Yeah.
apart from metallurgy. This is the one thing. And second thing, the maximum temperature of these alloys are 350 application temperature. And you have done a lot of working on 475 embrittlement. How does it going to help the actual users, this 475 embrittlement work?
Yeah, see, 475 embrittlement I speak about because many of the people deal with thin wall castings. So when we are doing some repair work or removing the riser and gating system in thin wall casting, we subject the material to high temperature. Whatever the cooling method we use, even if we do some water pouring and do the cutting, there will be a localized higher temperature which is experienced by the material. So when the material is subjected to because anyhow the material is not going to be on 850 degrees Celsius, however it can go up to 500 degrees Celsius. So it means that from the cutting point, there is a point where 500 degrees Celsius is exposed. So it means that from 1000, 900, 800, 700, 600, 500, 400. So there is a temperature where the material is also exposed to 475 degrees Celsius. But we always say only because of cutting, high temperature exposed, sigma phase formed, cracking came. So this is what the overall picture we see. But there is also a temperature which is creating a problem, which is 475 embrittlement. So that is very important to understand during welding of the material, during riser and gating system removal time. So that is why I try to explain the same. And also I mentioned that chemistry is one of the solution to control the sigma phase. The other solution is to play with the heat treatment. So if we are not able to control the chemistry, then the only option I have in a metallurgist hand. Whoever the metallurgist, he has two options in his hand. He deals with chemistry and he deals with heat treatment. So once he is not able to control with chemistry, then his second option will be with heat treatment.
Thank you. Thank you, Mr. Aditya.
Thank you, sir.
Can you have the memento for the speaker? Well, friends, the next speaker was in fact Mr. V.N. Satyanarayan from DISA, India. But Mr. Per Larsen has come all the way from Denmark to present this particular paper. His designation is Innovation Manager, the company DISA, Denmark. His educational qualifications are, he holds Master of Science in Foundry Technology and PhD in thin wall ductile iron castings, and he has got experience of almost 26 plus years of DISA line. His topic is making aluminum castings in green sand, exploring the benefits and challenges. Mr. Per Larsen, the floor is yours.
Thank you very much for the introduction. Let me try to start this. So, thank you very much. The topic for today, that is non-ferrous castings produced in green sand. And today we will talk about aluminum castings and brass and bronze castings produced in green sand. We have produced a small agenda for today. First, we will start with a short introduction. Then we will say a few things about molding and sand plants. And then we will talk a little bit about pouring. And then we will show quite a lot of examples of aluminum castings successfully today being produced in green sand. Furthermore, we have prepared a number of examples for brass and bronze castings, also today successfully produced in green sand. And then finally we will conclude. So let's jump to the introduction. I think everybody accepts that green sand molding, and especially virtually green sand molding, is a very, very efficient way to produce iron castings. Both producing aluminum castings and brass castings in green sand can also benefit from this very high cost efficiency that iron castings benefit from today. Many non-ferrous castings are already being produced in green sand today. For instance, if we look towards the US, we will see a lot of foundries both producing aluminum in green sand with success and brass and bronze in green sand with success. Unfortunately, this is not so widespread yet, so today we would like to give some details on how this can be done. So, in general, these non-ferrous castings, meaning aluminum castings and brass and bronze castings, are normally not made in very high volumes. Hence, we will try to focus today on solutions that are more suitable for producing castings in smaller volumes. If we look at producing non-ferrous castings in sand molds, there are a lot of benefits. Of course, they depend on which process the castings were produced in before. So the list I will show you today on benefits can be seen more as general benefits and covering most of the different processes. But of course it will be specific due to the specific process that we have converted into a green sand casting. So first of all, when we talk about green sand molding, we have this very high efficiency that is hardly found in any other process. Then we have a very simple and efficient core setting that will mean we can produce castings still at a high rate, even though they are cored. Then we have the chance to change tooling, meaning pattern plates, very fast. When we in the green sand process want to produce another part, we only need 1 or 2 minutes, then we are ready to produce the next casting. Depending on the need for service life of the pattern, we can choose many different materials. So we can use everything from hardwood to tool steel patterns, depending on what tool life is needed. And this means, of course, also that the costs for tooling can be kept very low and in proportion to what is needed. If we only have to run short series, we can produce the patterns in hardwood. If we need to run extremely long series, we can produce the patterns in tool steel. So these pattern plate lives can be very high, and as high as 500,000 or even more if we go for tool steel. This means at even very high production volumes, we only need one set of production patterns. We don't need a number of toolings to be able to make the production. Furthermore, the pattern maintenance will be very low when we compare to other processes from which these castings normally are moved. We do not have to repair weld on a die every 5,000-10,000 shots or something like that. We can use the pattern for hundreds and hundreds of thousands of molds if we produce them in the right material. Furthermore, as the tooling normally is quite simple, the lead time from a 3D CAD model to the first prototype can be very short, and of course also the lead time to the start of production can be very short too. If we need to do modifications, optimize the gating systems or feeders, it's also very easily done on a pattern for green sand molding. So some of these points will be discussed in this presentation. Unfortunately, the time is a little short, so we will only highlight some of the features. So moving on to molding and sand plant. If we are going to produce aluminum or brass and bronze castings in green sand, the molding machine will be exactly the same. This means we have a proven and very efficient technology available. If we look at aluminium, then we will see that the tendency of penetration will be more or less the same as for iron. And this is because the wetting is much stronger for aluminum, but on the other hand, the density of aluminum is much less. So at the end of the day, we will have more or less the same tendency to penetration of aluminum as we have for iron. And this means that we can get very good surface qualities of castings coming from green sand molds, even though we use sand as molding material. If we look at brass and bronze, we will see that the tendency to get penetration is quite a lot bigger than for iron. To mitigate that, we normally recommend molds with lower heights, let's say 400 to 480 millimeter, to have a lower risk of getting penetration on the castings. If we look at the molding sand we use for aluminum and brass and bronze, we use quartz in both cases, and as with iron, we use bentonite and water to bound the mold. Properties for molding sand will be similar to the molding sands used for iron. Typically, we are not using coal dust when we produce aluminum and brass and bronze. Properties of the molding sand will of course have to be adjusted a little bit to the actual application, meaning are we pouring aluminum or are we pouring brass? In case we are pouring aluminum, we will try to keep moisture a little bit on the low side to reduce the risk to get hydrogen pickup. Are we talking about brass and bronze? We will try to keep the grain size at a lower level to reduce the risk of penetration. Core setting will be done in the same way as you know from iron foundries, meaning we have a proven and very, very efficient process. So running core castings is actually one of the places where moving to green sand will give you the best benefits. If we talk about aluminum castings and brass and bronze castings, we typically talk about shorter volumes. This means it can also make sense to do core setting by hand. Doing core setting by hand, we can also set very, very complex cores. We can use nails for fixing the cores in the molds, etc. We can also set non-glued core packages if we would like to do that. We can even use two operators, one from each side of the machine, to speed up the setting of the cores into the mold. So with this setup, and even though we use manual core setting, we can easily run 100 molds per hour without too big problems. We can of course also run the molds horizontal and use a match plate machine to produce the molds. And again here, as we saw for the vertical molding, we will use proven technology being used for iron for many, many years. If we look at the sand plants, typically you will see a sand plant as quite a big installation and also quite a costly installation. But are we talking about these smaller production volumes? We don't need to go for these big and costly installations. For say 100 molds per hour setup, we can use a much, much simpler installation and hence also a much, much cheaper installation. And here we see an example of a simple sand plant suitable for around 100 molds per hour. This of course also means that it will take up less floor space, and what is even more important, that total investment will be much smaller both for the sand plant and also for the molding machine. So actually it will match this smaller production capacity. Molding, especially when we talk about vertical green sand molding, people normally think 300 molds per hour, 400 molds per hour, even 500 molds per hour. But when we talk about modern green sand molding, we now have available solutions that both fit these huge volumes normally produced in green sand and also smaller volumes which are relevant for non-iron castings. Here we see a list of some of the available molding machines. We have the D3, which is one of our high runners with up to 555 molds per hour. And then we have a new group of molding lines with the C line, a vertical molding line, which speeds from 150 molds per hour and up. There's also new and smaller match plate machines available, which suits very well the smaller production volumes normally seen at these non-ferrous castings, meaning both aluminum castings and brass and bronze castings. So we can say that now we have modern and affordable molding equipment available that also suits these smaller production volumes. And of course also the investment will follow this. Okay, let's move on to pouring. For most aluminum castings and brass and bronze castings, hand pouring is a good choice. It's a simple way to pour the mold and very flexible way to pour the mold, and most of these castings can easily be poured this way, and it matches very well the smaller production volumes normally seen for these castings. Are we talking about aluminum? Sometimes it's a little different. Aluminum forms oxides very fast, and these oxides, they will reduce mechanical properties. And in case we are producing aluminum castings where we need to obtain the highest possible mechanical properties, it is super important to reduce the formation of oxides to an absolute minimum. This means we need to have a laminar flow, and we need to avoid splashes of the metal, etc. We obtain this by using low pressure pouring, where we fill the metal through the side of the mold and slowly fill the metal into the mold. To get high productivity, we have a small core closing the runner bar, meaning we can move away from the mold with the pouring device before the metal is solidified. And how does that look in real life? Here we see the mold, we see the nozzle on the pouring device docking to the side of the mold, and we see these small cores we use to block the runner bar when the mold filling is over. This is how it looks in real life. We do mold transport, we dock to the side of the mold, then gently we fill the metal into the mold, and when the mold is completely filled, we close the runner bar with this small pneumatic cylinder pushing the core into the runner bar. We can move away, do mold transport, and then pour the next mold. So even though we have this system, we can still reach quite high production speeds. This will of course mean that we have no manual interactions in the in the pouring. So we are not relying any longer on skilled persons pouring the molds, and we can also save personnel in the foundry. Here we see a picture of a pattern where we see a very simple gating system needed for this system of bottom pouring. So this was a little bit about the technology that we use to produce aluminum and brass and bronze castings. Now let's try to look at some examples of castings produced with success today in green sand. First of all, we have to say when we talk about aluminum castings and green sand molding.
Last 3 minutes.
3 minutes, perfect. When we talk about green sand molding, then most of the castings are moved from gravity die or low pressure die. We can say many of these castings can be moved to green sand molding. And if you have any doubt about castings possible being moved to green sand, then please don't hesitate, contact us. We have the DISA team of application engineers that will analyze the parts, and then we can find out together if we can convert these to the green sand process. So let's look at some examples. Here we have a cord casting, a tank inlet produced in Denmark, a bearing sheet produced in Germany, ventilator wheel also produced in Germany in green sand, pneumatic control valve. So now we move into a little more demanding castings. This casting will demand pressure tightness. Another casting that will demand pressure tightness. We can also do aesthetic castings. If we take a little bit more care about the sand parameters, we can reach super good casting surfaces. So even aesthetic castings can also be produced in green sand. Here we have an example of a hydraulic block where we have requirements to pressure tightness, and we also have requirements to the mechanical properties. A connector for a fire hose, a critical part. Of course, this part cannot break in operation when it's part of a firefighting system. Gas valve, also a casting produced successfully in green sand, and also a casting where we need pressure tightness. Compressor housing. Then some bigger castings, clearly also bigger aluminum castings are being produced successfully in green sand. Here we have an example of a 10 kilo casting, another example of quite a big casting. More complex castings can of course also be produced in green sand, like this heat exchanger. Then a manifold. Of course we know that e-vehicles are taking over, but still a lot of ICE vehicles are being produced. So for instance, here we have a manifold being produced in 7 million pieces in France with great success. Transmission housings can also be produced in green sand with great success. Last but not least, also more demanding castings with higher requirements to the mechanical properties can also be produced in green sand if that is needed. So that was aluminum. Let's try to look at some examples of brass and bronze castings also being produced successfully in green sand. And I guess one of the most typical castings will be fittings. A lot of fittings are produced around the world in green sand on dymatic lines like this one, which is produced in the US. Different covers are also produced successfully in green sand all over the world. A valve body actually produced in my home country on a small dymatic. Another valve, a little bit more complex, but as we talked about earlier, setting cores in the green sand process is normally quite easy, so making these castings with more complex cores is not very difficult. A last example, impeller, and then a further example of aesthetic casting also. This is the body for a lamp, where we need a super good surface quality, and that can also be obtained in green sand if we again pay a little extra attention to the sand properties. So let's try to move to the conclusion. So what we know is that green sand molding, and especially vertical green sand molding, has proven to be a very cost-efficient way to produce iron castings. I think nobody will argue that. But we can also see that this cost efficiency can be transferred to both production of aluminum castings and brass and bronze castings. And we have shown that with, I think, quite a number of casting examples shown today from different places around the world. So I think we can say that both aluminum and brass and bronze castings can be feasible produced in green sand molding, and that we now have modern molding equipment available that matches these often smaller yearly quantities which these castings are produced in. So I think with these words, that was the end of my presentation.
Thank you. Thank you, Mr. Paglas. Since we are running short of time, I would like, if anyone is having any query, you can talk to the speaker, because the next technical session is to start by 12 o'clock. Can we have the mementos, please? Thank you very much for your patient listening to the speakers. We will have the next technical session now.
Hello. Yeah. I would request Mr. Suresh Chavan to felicitate Mr. Sushil Sharma for conducting this session. Thank you, everyone. We will be starting the next session in next 5 to 10 minutes.
Sri V.K. Purohit ji, and Speaker Mr. Vinay Godge and Jitendra Lakhotia ji. Today's Session Chairman, Sri V.K. Purohit, is a graduate in metallurgical engineering. He has worked in Hindustan Gas Limited. Previously, he was working as a Chief Operating Officer, Foundry Division in Chorus India Limited, Pune. He has exposure to grey iron, malleable and AGRN. Experience of over 60 years in foundry industry. I request Mr. V.K. Purohit to conduct this session.
Thank you, John, sir. Hello, good afternoon, everybody. In this session, we have two renowned speakers in their respective field. First is Mr. Vinay Godge, who is a Vice President Business Development for Forens Polymers, Haridwar. And he is a graduate metallurgical engineer and having the experience of ferrous and non-ferrous foundry, about 35 years. And he has a vast experience of renowned company like Fosico, As Chemical, Gargi, and he has published a lot of papers on, especially on refractory coating and sand additives. And Mr. Jitendra Lakhotia, who is a CEO from Akar Foundry, Pune, and he is a director and partner of Akar Dyes and Mold also. And he is basically commercial and MBA marketing from Pune University. And he has received the Best CEO Award from ACMA Lean Cluster during the Greece Cotton Terrier. And he has worked in Jain Foundry, also MTech and Akai Castalloy. So now I would like to request Mr. Vinay Godge to share his views on in-situ coating preparation.
Good afternoon, gentlemen. Thank you, Mr. Purohit. Before I start my presentation, thanks to 70th IFEX Organizing Committee and also Technical Paper Committee for giving me this opportunity to present this paper. In situ coating preparation, a latest trend in refractory coatings with cost-saving opportunities for automotive and jobbing foundries. I'll just go through a background because it's required. See, in the mid of 20th century, most of the iron foundries rather were using refractory coatings in the powder form only. The foundries used to get refractory powders like zirconium, graphite, and they used to use either dextrine or bentonite as a binder, soak the powder in the binder overnight, and then use a mixer or even a small mixer so that they can use this coating. And mostly these coatings were being used by either brushing or by swabbing, and seldom by spraying also. Technological change. In the later part of 20th century, foundries started modernizing and the automation came into picture. So the automation was not only in terms of molding and core making, the automation was there in coating process as well. The foundries started adopting modern coating processes, coating practices rather, like dipping, flooding, or the conventional practices such as brushing and swabbing, because of the consistency in the coating parameters and because of high productivity. The coating methods such as brushing, swabbing or spraying, it requires definitely skilled operators and also time consuming as far as productivity is concerned. Whereas the processes like dipping, flooding are highly productive and the operator skill required is relatively low. However, such coatings are specially designed with adequate rheological properties in order to control the wet film thickness, coating penetration, flow properties, etc. And keeping in mind these requirements, ready for use coatings were developed. That means coatings in ready for use or paste form. And then these coatings become very popular. So the present scenario in refractory coatings is most of the coating suppliers supply coating either in ready for use form or in paste form. Then subsequently on the shop floor, these coatings are diluted to the required application consistency for dipping or for flooding. And such coatings are normally supplied in 30 to 40 kg plastic carboys or buckets. What are the pain areas in present system? The buckets and carboys warpage during transportation, leakage, spillage problems during transportation, settling sedimentation issues, perennial problem, large storing space because the buckets need larger storing space for storage. Bacterial attack on longer storage, especially in the high temperature ambient conditions, the bacterial attack is quite fast. And shelf life issues. In the sense, normally most of the water-based coatings have about 6 months shelf life, but in case of ambient conditions, very high temperatures, the bacterial attack can be even faster. Too much of handling of the buckets. Most of the automotive foundries or the bulk coating consumers, if you see, they use coating to the tune of 30 to 50, 60 tons per month. So the number of buckets handled are quite high. And that's really a non-value added job. And of course the high packaging cost. When I say high packaging cost, the kind of water-based coatings being used by most of the automotive foundries for general purpose and for critical applications, these coating priced are such that about 15% of the selling price of the coating constitutes packing cost. So what is the new trend now? The coating can be supplied in powder form. It will be supplied in about 25 kg bags, very easy to handle. Coating will be manufactured in foundry premises. And day-to-day manufactured fresh coating will be distributed to core shop for use. Coating manufacturer normally along with the product they will supply you a coating mixer because such kind of coatings cannot be made by a normal homogenizer mixer which is commonly used by foundries for homogenizing the coating after dilution. This kind of powder coating requires a special mixture with a special stirrer design or blade design. These are kind of mixers we provide. The coating will be supplied, as I told you, in powder form in about 25 kg bags. And we also supply a mixer for coating manufacturing. The coating supplier will also train the workman for manufacturing, testing the coating on the shop floor. This is required for the initial purpose. Once the parameters are set, then it's a stereotype operation. And the fresh coating will be supplied day to day. The support required from foundries for this is allocation of a suitable space for mixer installation so that the product handling is much efficient and better. Laboratory for initial testing purpose till the parameters are standardized, and manpower for coating manufacturing. What are the advantages of using powder coating versus ready for use or paste form? Is the supply of coating in just in time, the fresh lot every time, so there is no aging, no bacterial attack, no shelf life issues. And the most important from storage point of view is less than 50% of the storage space is required, because these are all bags which can be stacked one over the other. And the powdered product has a shelf life of 1 year, and unless it is tampered or it gets mixed up with the water, the product doesn't deteriorate. So there are absolutely no shelf life issues for the product. And the most important reason for using powder coating is substantial reduction in the price due to elimination of packing material. Packing material normally in such kind of coatings, it acts as a means of transport of product from one place to other place. It doesn't really add any value to the product. So if we are able to eliminate, then we are able to pass on that benefit to customer. We'll just look at the financials. Presently, most of the foundries use aluminum silicate ready for use coating with a landed cost around say 31-32 rupees a kg. The powder coating which we now will supply or will offer you, it will have a budgetary price of around 54 rupees per kg. This price may vary based on the product used by foundry to foundry, but roughly around the same price. 1 kg of powder coating will yield 2 kg of ready for use coating. So the effective price of powder coating will be about 27 rupees per kg. Hence, the saving in RFU coating itself is about 4 rupees per kg. Now in this, you can slightly add certain things like electricity used by foundries, but the electricity used is very, very nominal. The cost of electricity cannot go beyond 5 to 10 paise per kg. It is hardly about 3 to 4 units per day, and so it's very, very nominal. The manpower which is used for making the coating, normally in most of the automotive foundries, they have allocated a man who prepares the coating and distributes to the coating tank. The same man can be used for coating manufacturing, so there is no additional cost involved. So if a foundry is using about 30 metric ton coating per month, then the saving will be around 1,20,000 rupees, and the saving per annum will be over 14 lakhs, which is substantial for the kind of for the cost of coating what we are using. It will be around 15 to 17%. So here I have considered the saving in, considering the electric cost, instead of 14.4 lakhs, it will come to 14.3 lakhs. So the electricity is not very substantial, which can affect the cost of this thing. Benefits will be substantial. Now I'll just go through the field trials which we have taken so that it can give you an idea as to how versatile will be the product. This trial has been taken in one of the foundries where the casting is a small volute core. It is a foundry producing automotive casting, turbocharger castings, and the trial was made with about 200 kg coating. The application viscosity was about 15 seconds, and the application process was dipping. and the wet film thickness we got around 225 to 250 microns. These are the cores coated with powder coating made in situ. And this is the casting photograph where you can see the clean casting. The second trial which we have taken is again a critical casting. It's a water jacketed 2-cylinder block, and we have this in the here also the coating is used by dipping process. Viscosity is around 14.5 seconds, and these are the cores which are dipped using the product, and this is the casting finish what we have got. The third trial we have taken is one of the foundries who are producing bigger castings like transmission housing weighing around 175 kg. And the coating is used here by flooding process. So first was dipping, this is flooding process. You can see the cores coated by flooding. Here the wet film thickness was around 200 microns, and you can see the casting finish inside. It's absolutely clear, no sand sticking. One more trial of transmission housing only, but here the coating application is by swabbing. You can see the core being swabbed in the first photograph, and in the second photograph the coated cores, and you can see the casting finish inside. It's absolutely clean, no sand sticking. This is coating. The 4 trials photographs what I have showed you, it was aluminum silicate water-based coating. Now the trial which I am going to show you now, this is a zircon-based coating which is used on a larger castings. This was trial that is one of the big foundries. The casting weight was about 3.5 tons, and the product was used by brushing application. The as-made coating Bome was over 100, which was then diluted to about 75 Bome for brushing. Specific gravity was about 1.95. These are the molds which are brushed with zircon-based coatings, and the casting is, it was not possible to collect the casting photograph, but the casting was very clean, and the casting was already left to the customer, so we could not collect the photograph there. So benefits to the foundries using powder coating technology is just-in-time supply of coating, fresh lot of coating every time, no bacterial attack, no shelf life issues, very less storage space required, and substantial cost savings, which is most attractive to most of the foundries. So to conclude, from the trials what I have shown above, it is evident that the in-situ coating preparation using powder coating technology not only helps foundrymen to use it on all types of castings of any size, it yields substantial cost savings as well, which will help the foundrymen to increase their profitability. Thank you. This was my presentation.
Yeah. Any question, please?
Hello. Yeah, my name is Brijesh and I'm from Siemens. I have 2 questions. First question will be for the full mold casting process. Any specific refractory coating is required in comparison with sand castings? And my second question is, as you saw on that surface finish, so by coating method or different kind of coatings will improve the surface finish, and how?
See, I'll answer your first question. See, for full mold process, the coating required is definitely slightly different than what we use for sand casting. Number one, in full mold process, the coating has to be highly insulating, And number two, the coating has to be a good permeable coating, because in full mold process you don't remove the EPC pattern material, and when you pour the casting, EPC burns out and produces some kind of little slag which should ooze out from the coating layer, otherwise it will give you inclusions in the casting. So definitely that coating calls for a different type. It is not regular coating used in automotive applications for dipping or flooding. Second thing is these coatings are used with a little bit higher bome, because the coating thickness is typically used in automotive foundries are anywhere between say 200 micron to 500 micron depending upon the criticality of the casting. But in case of full mold process, the coating thickness is anywhere between 1 to 2 mm, or sometimes even it is 3 mm if your casting thicknesses are very high. So the coating is totally different and it has to be designed differently. Your second question, can you please repeat again?
The type of coating and different coatings, can it will be improve that surface finish of the casting, and how?
See, surface finish of the casting depends upon two factors. One is the AFS of the sand what you use, and another is the refractory coating. Okay, so definitely refractory coating will help you to improve the surface finish, no doubt about it. In any process you use, whether it is a sand casting, LFC process, or even your full mold process, coating will definitely help you to improve surface finish. Normally, if you see the sand casting process, people use sand, AFS anywhere between 40-45 to 55-60. So when you use coarser AFS sand, and if you do not use coating, then you will definitely get a rough surface of sand finish. So just to make the surface more smoother, and you should have one layer of refractory material between the mold and the metal, which is probably having a more refractoriness than sand. That will help you to give you a clean and good casting.
And type of coating like brushing or spraying or dipping, is any difference in that surface finish, or
yes,
which will be better?
Definitely, definitely. See, normally surface finish, if you obtain with flooding and dipping, are much better compared to brushing and swabbing, because brushing, swabbing or spraying, these are skilled operating processes. So you need skilled operators for this. Whereas in case of dipping and flooding, the coating rheology is set in such a way that the processes are stereotyped, and it will give you consistent uniform layer thickness everywhere. Suppose you have like if you talk, I don't know whether you have seen a motor body casting where there are the fins which are deep to 2 to 3 inches deep. So there the brushing and spraying won't help. The flooding helps there. And second thing is productivity. Brushing and spraying will give you very low productivity. If you are into mass production, then dipping, flooding, these processes will help you to get very good productivity.
I am talking about that bigger casting, weighing maybe more than 5 ton.
For that, brushing is the only way. Even more than 5 ton castings are also flooded. There are people who are using flooding for more than 5 ton, 10 ton casting also. It depends upon, which processes your foundry is going to adopt.
Okay, thank you.
Any further question, please? Yeah, Vinay sir, I have one question.
Thank you very much.
I have one question for you. Of course, coating is required and it is beneficial for the surface finish and all. But what are the precautions or the disadvantages of using coating? Or what care we should take?
I don't foresee any disadvantages of using the coating, but precautions, what you said is absolutely correct. See, there are 2-3 times. One is you should use, especially for critical castings like block and heads, you should use coatings which do not generate much gas, number one. Number two, you should use coating which has got adequate permeability so that when you do the casting, if there are any gases in the mold generated during pouring, these gases should not only pass through the vents, but they should pass through the coating layer also. Second thing is, whenever you are using this coating either by dipping or the flooding process, the coating parameters which are set as per SOP, one has to follow those parameters very strictly so that you get consistent results casting after casting.
Thank you. Thank you.
Thank you very much.
Thank you, Mr. Vinayak, for your presentation. I would request our session chairman, Mr. Purohit, to felicitate him for the presentation.
Now I would request Mr. Jitendra Lakhotia to present his paper on aluminum, demand of aluminum casting for EV. Now EV is a very popular and buzzword in foundry industry because of it is going to impact the foundry industry overall. So I think he will give a insight about what are the changes and which sector is going to get benefit and which sector is going to have some changes. Please.
हेलो इट्स हाथ नहीं लगाना Good afternoon. Thank you, Purohit Sahab, for my introduction. Thank you, IFC committee, for providing opportunity to present the paper. And thank you very much, technical committee, technical paper presentation committee, for your help and support. EV, electrical vehicles, is buzzword, and it's like coming with a tsunami in automotive field. The disruptions which will be caused by EV are enormous, and most of us are clueless on this, what will happen. So I will go ahead with my small presentation on this. This is my introduction. Since last 28 years, I am serving aluminum foundry industry. In this presentation, I have covered topics of climate change, global challenges, how there will be transition for EV, and why EV, how governments are promoting it, subsidies, then how the aluminum consumption in electric vehicle will change, and what should be the future strategies for aluminum foundry. So we are part of, Akar Foundry is a part of Vishwakarma University. We are around 60 million US dollar turnover company, and 35% business comes from Akar Foundry. We support our customer from prototyping to serial production. All facilities are in-house from proto to serial production, everything. Our EV journey started in 2015 when we first produced some part for Mahindra Gen Z vehicle and it was sold in United States, Silicon Valley. So we produced headlamp housing and its assembly structure. Now we are also supporting in two-wheeler with a customer named Torque. They have recently launched motorbike, first motorbike of India. We also got new business from Bajaj Auto for their Yulu project, which is like a moped, TVS moped. It is similar to that. Our serial production for Tata Motor EV Tigor, which is produced in Sanand and Gujarat. So we have started its production since last 6 months and we are also supplying parts to Mahindra Electric for their KUV electric vehicle. Here you can see some images on this, how the part looks like. All are in aluminum castings in a process, gravity, low pressure, high pressure die casting. Recently there was a World Committee, all leaders in Davos, they have declared their net zero carbon emission. We know transport industry contributes one of a very large extent of carbon monoxide and carbon dioxide, which creates health issues and also it is killing the environment. So EV push from the world leaders is natural. India had committed a long time frame of 2070. Some countries, they want to be carbon neutral by 2030. It looks like this EV sales scenario up to 2050. So there will be all types of vehicle, but the gradually conventional fuel and its demand for the automotive will reduce. Hybrid vehicles will be there, but electric vehicle, it looks like that it will be in full throttle. And there will be an entry of hydrogen fuel cell also. In this slide, I had tried to capture OEM's plan, how they want to convert their cell and how would be the electric cells in their total vehicles production. We know that Scandinavian countries are now front runner to introduce EVs and most of the new purchases for car in Norway, Finland, Sweden, they are in EV form only. European leaders had committed that most of them want to bring electric cars by 2030. To make EV happening, there are various subsidies provided globally by each country to their OEMs with the incentives for infrastructures, monetary benefits. This is how India will go. By 2030, 80% of our two-wheeler and three-wheeler, they will be in EV. 70% cars, commercial cars will be in EV. 40% of buses will be in EV. And 30% cars will be in EV. This is information we took from Niti Aayog, their own records. In India, we are frequently going through the word PLI scheme, and more than 20 OEMs have been approved under this PLI scheme, in which cost reduction of EV will be feasible. And government is providing import-export duty concessions to boost domestic manufacturing of EV. From 2015, India is working on the subsidies through the FAME 1, FAME 2 policies to provide tax benefits for manufacturers as well as end customer. Even bankers are providing cheap loan, and all are trying to boost EV sales. You may also know that our government, our Prime Minister Modi ji, never uttered a word about IC engine. He always say about EV and various plans on green energy. The challenges of EV revolution in India are huge because of the size and demography of the country, unavailability of charging structures, infrastructures, driving range of a car. Still we are having around 300 kilometers driving range. Recently Tata launched Nexon with 400 kilometers. Electric cars are very costly than conventional cars. Battery replacement is huge cost. And disposal of lithium and zinc batteries is also a question mark. Disposal will be at a risk with a prolonged effect of soil deterioration. My presentation is more on aluminum casting. So here aluminum foundries can feel safer. As estimated, there will be no major impact on aluminum casting suppliers' sales. So as the battery weight is more, everyone wants their EVs to have a lightweight alloy, which will add strength. Then aluminum is recycled. It is sustainable and energy efficient. So most of the steel parts, ferrous castings, can be replaced by aluminum castings. So 45% of aluminum will eventually be 60% of a total vehicle. This is simple diagram wherein you can see which parts will not be required in EV. Some parts will remain unchanged, and there will be new parts like battery enclosures, mounting brackets, then motor enclosures, covers, ECUs, all this will be required. As I mentioned earlier, some of these parts we have already started production for Tata, Mahindra, Bajaj Auto. This is one schematic diagram of a car, how EV will work, means how the components will be placed. See, charger, batteries, controller, transmission. So, very few parts. Normally, car require around 300 parts, and it will get reduced if a engine, I would say, from 200 parts in an engine will get replaced by 30 parts. So it will be a huge challenge for foundries. These are the aluminum components where the aluminum content per vehicle is mentioned. Battery box, the biggest part of aluminum in the new EVs. Body enclosures. This is also an interesting story. Tesla, which come up with IDRA to produce 6,000 ton gigapress. You can see in a diagram that so many parts in Model 3 are now replaced in one casting, which offered 10% weight reduction, and 70 parts were reduced with the new technology. They have developed a new alloy also. This is the last slide of presentation. What aluminum foundries will have to do? Since last 28 years I am in this field, and most of my experience goes in business development. I can sense that risk of idle capacity for big foundries will be big risk. Capacity will remain idle. Very means parts like engine covers, transmission cases will reduce. Now around 75% of our India's electric, vehicle sales is two-wheeler, and 80% of two-wheelers will be in EV by 2030. By 2025 it should be around 40 to 50%. So the big suppliers which are carrying the presses of a size 250 ton, 400 tons, 660 tons like this, they will have huge idle capacity with them, and this can be a problem for the upcoming new foundries, small foundries. Foundries will have to go with a new product mix. Akar Foundry changed its product mix from 80% automotive, 20% non-automotive to 55-45%. So this will be the reality. Very quickly, non-auto segment business must be taken by the aluminum foundries. Those who are dependent on two-wheeler have a major threat. They need to move swiftly. There will be many aluminum structural parts will be coming, which will require high tonnage press. So the demand for good high pressure die casting machines will be bigger. For a player, one of my friends from Noricon is here, so they will have a good thing for here to sell their big presses of Ital press. Development of new alloys which will have a better strength. Technology will have to be upgraded to cast thinner part. Now it is around 3 to 4 mm customer may demand 2, 2 mm to 2.5 mm general wall thickness. And all this will call for simulation of lightweight parts. So digital awareness and digital adaptation will be also a challenge for the aluminum new foundries. Thank you very much. If you have any question, I would be happy to answer if you have any question.
Yes, there is a question here.
Hello, sir. I have a question. Since Akar Foundry have all the various kinds of processes under one roof, that means PDC, LPDC, GDC, tool room. So in a near future, in next 5 years, let us say, which of the processes will have more and more demand?
I guess the ratio of high pressure would be around 80%, and in balance 20% it would be low pressure die casting around 12%, and 8% will be gravity die casting. Gravity die casting will be more suitable for alloy wheels because most of the Japanese companies make alloy wheels in a gravity. However, European companies make in low pressure die casting. But the battery boxes for a customized cars like Bentley, Aston Martin, where the volumes will be less, I think that low pressure die casting will be preferred process even though it is costly on part price. But the high volume cars, they will prefer big press of 3000 ton and above. I hope you are looking for these issues.
Thank you, sir.
Thank you.
Any more questions?
I believe this was last presentation.
Yes, yes.
Thank you.
Thank you, sir. I would request Mr. Purohit, our session chairman, to felicitate Mr. Jitendra for presenting his paper. Hello. I would like to thank Mr. Vinayak and Mr. Jitendra for participating in the tech sessions and being a part of the 70th IC and IFEX 2022. Your presentation was quite insightful for all our Foundry men who are present here today. Now I request our OC Secretary, Mr. Suresh Chavan, to come on the stage and felicitate our session chairman, Mr. Purohit, for conducting the session. Thank you everyone once again. The session ends here. The lunch is ready, so you can have your lunch now. Thank you.